Hello wonderful person, this is Anton, and today we're going to start this video with this beautiful image you might have seen before in stunning photos taken by astronauts from space. With this one taken extremely recently when the International Space Station was flying over Chad. And this is the image of Lake Idaho. And well, as you can see from this image, it appears as a giant silver mirror from space. This is a phenomenon referred to as sunglint. It essentially happens when sunlight reflects off the surface of some kind of a liquid or some kind of a very smooth surface, in essence acting like some kind of a mirror. Here's a rough representation of how this unusual phenomenon works. But sunlight in this case isn't just a beautiful photographic effect, it's also been investigated in a lot of different studies as a real phenomenon that could be used to find liquids on other objects, including exoplanets. Because this is a key indicator for finding liquid water and can be visible from very far away. Which is precisely how back in 2009, by observing the images from the Cassini probe, researchers became absolutely convinced that the Saturn's moon Titan almost definitively has some kind of a liquid on the surface. And though back then it was not certain what liquid, eventually it became pretty clear that it seems to be large bodies of ethanes and methanes that we've discussed in a lot of previous videos that you can find in the description. And while in this case detecting these oceans and detecting these lakes is one of the most fundamental goals of modern astronomy, mostly because this is the main target in the search for extraterrestrial life. And so in order to discover life beyond the solar system, and in order to confirm potential habitability of some kind of a planet, we have to find bodies of liquid water. And it just so happens that this might be the best way. And so let's discuss some of the recent discoveries about this, focusing on some of the recent studies and recent discoveries. But I guess the question is, exactly how could we use this cosmic mirror to uncover hidden oceans billions of miles away? And what does it tell us about potential planets' habitability? Well, at its core, sunlight is about specular reflection. And here you have to imagine a perfect mirror. It reflects light in a single precise direction. That's basically specular reflection by definition. Now imagine some kind of a rougher surface, such as a matte wall, that scatters light in all directions regardless of the incoming angle. In science this is referred to as lambertian reflection, a type of a diffuse reflection where the surface starts to appear equally bright regardless of the viewing angle. And the best example of this reflectance would be something that's, for example, covered in varnish. A varnish wood will usually have this unusual glossy coat, creating more highlights when viewed from certain angles. But when it comes to various stellar objects, so for example moons and planets, this type of reflection can actually be used to determine what's on the surface, or at least what type of a material the surface is made out of. So for example, land masses or extremely rough oceans will usually have much darker appearance when observed from certain angles. But if the conditions are calm and if the body of liquid is smooth, it's actually going to act like a mirror. Here's a really good example from the Hawaiian Islands. But this bright glint is only observed when the planet and the star are perfectly aligned. And so here the angle of observation is very important. And in most cases this is easily visible to astronauts on the International Space Station or to various satellites taking photos, which makes it very easy to tell if we're looking at relatively smooth water or water containing rough patches. And this somewhat common effect can even reveal interesting ocean and atmospheric features that would be otherwise extremely difficult to see. Here we're talking about patterns on the water and even in the atmosphere, including the formation of various atmospheric gravity waves that either roughen or calm the surface water below. But it's crucial to understand that sunglint is not exclusively a sign of water. It simply represents a smooth liquid on the surface, but the liquid can be made out of anything, with a famous example in this case once again being Titan. And so this beautiful 2009 picture from the Cassini spacecraft confirmed the existence of very large seas that seem to contain liquid hydrocarbons, but practically no waves. With later studies discovering that for some reason, titanium seas and titanium lakes seem to lack the presence of waves, suggesting that the winds are very likely extremely weak. But much more importantly, this was a direct confirmation that glint is a strong indicator of liquids, which in certain conditions can of course be water. And that's of course one of the main drives in modern astronomy, trying to discover liquid bodies of water somewhere out there, and specifically on some kind of a distant exoplanet. And that's because liquid surface water is widely considered to be a fundamental prerequisite for life as we know it. And so discovering glint around some kind of an exoplanet in the habitable zone of some kind of a star may serve as a direct pathway to potentially finding extraterrestrial life. And the most promising way of doing this is, of course, direct observational methods. But first, an important side note on how we usually study exoplanets today. This is usually done with what's known as transmission spectroscopy, a primary observational probe of upper atmosphere as a planet passes in front of a star and as the starlight goes through the atmosphere but is then blocked by certain aerosols and certain molecules, changing the starlight just a little bit. And this often presents us with a graph that looks something similar to this. It reveals starlight with certain wavelengths missing. And so then by taking these observations and comparing them to the ones we have from various labs where very similar experiments try to produce very similar absorption spectra, researchers can start deducing what we're seeing around this planet. And though it's not always 100% accurate, this is one of the best ways to detect things like, for example, water. And so let's say we found a planet where water seems to be present, and a planet that can potentially host liquid oceans on the surface. Well, here at least a few studies propose that we can actually use multi-phase observations to possibly definitively discover bodies of liquid. For example, this study from 2019 proposes a technique that has not been used yet, referred to as multi-phase mapping. It essentially combines rotational mapping with various glint measurements that try to observe exoplanets several times with the assumption that the planet is also rotating. And so as this exoplanet rotates on its axis, it will create a kind of a time series of the reflected light showing periodic variability. And in theory, this could then allow us to form a longitudinal map of the planet's surface, identifying different types of terrain simply based on the brightness and the color. And in this case, certain strong reflections could potentially suggest presence of liquid water. In this particular study, they actually used Earth as a potential candidate just to model this and to see what happens. But the real trick here comes from observing the planet at multiple orbital phases, and specifically comparing the appearance in the quadrature phase, when the planet is half illuminated from our perspective, and the crescent phase, when the planet is barely illuminated at all. And so when the researchers used Earth as a potential sample, they've discovered a striking signature for locations on Earth where we know oceans are very large. For example, at crescent phase, the apparent albedo or brightness of ocean-bearing slices seems to increase dramatically by a factor of 5, and sometimes up to 16 times in cloudless conditions, with all of this contribution coming from that ocean glint. In contrast, land-bearing slices show almost no change in brightness with the phase, remaining relatively constant. And so this very apparent deviation from lambertian behavior seems to be a strong indicator of some kind of a liquid on the surface, and of course a strong indicator of ocean glint. And as the planet rotates, the glint spots appear to blink as less reflective continents interrupt the reflection of the star from the ocean on the surface. But obviously here we have one main problem: false positives. What if what we're seeing is just some kind of an artifact, or what if these brightening events are from the star itself? Well, the beauty of this technique is actually its robustness. For example, let's just say there are some clouds and hazes here that can potentially also increase reflectivity. The best example in this case would be something like Venus. Well, the simulations here suggest that the cloud effect does not correlate with any surfaces or any continents in the same way as glint. And so even though clouds might increase overall reflectivity, the glint effect is much stronger and is usually a lot more localized, producing something that looks very different. Okay, what about ice? What if there's actually ice on the surface, kind of like similar to Mars, that's reflecting in the same way? Well, here reflectivity will also increase, but the signal from glint is once again much stronger, very likely at least 3 times stronger than from the ice caps, which means that if we observe very strong reflections and reflections that are changing very fast, the only explanation here is once again some kind of a liquid on the surface, and very likely not ice. And so here these phase-dependent behaviors, combined with longitudinal mapping, can definitively differentiate clouds and ice from some kind of a liquid on the surface. And by observing this multiple times and by basically mapping this over and over, we can then also determine if this is coming from the planet or from the star. In other words, right now this method is one of the most promising methods for discovering some kind of a liquid somewhere out there. But obviously here we're not going to know if this is water, or just like on Titan, methane and ethane. And the only way we can assume that this is water is of course if this planet is orbiting close enough to the star to potentially have habitable conditions. Right now there are not a lot of exoplanets known to us that seem to have these conditions. and you can learn about some of them in the description below. But the next question, and I guess the main question, is of course, how would we even do these observations? And for this, we'll most likely need next-generation, high-contrast, space-based direct imaging telescopes equipped with star shades and coronagraphs. Right now these don't exist yet, but we have at least two that are still conceptual and might launch in the next 10 years. One of them is called HABEX, Habitable Exoplanet Observatory. Now this is still just a proposal and nothing has been made yet, and if it does launch, it's only going to be in 2035. We also have this telescope known as LUVOIR, or Large Ultraviolet Optical Infrared Surveyor, that's still just in the proposal phase, and if it launches, it's going to be in 2039. And Habitable Worlds Observatory, that's even in earlier proposition phase, that might become operational in 2040s. In other words, right now we just don't have the telescope required for any of this, but the idea itself could definitely work. Although I guess the question that you might be asking, or at least I was asking, was, okay, so why can't we use something like James Webb or even the Hubble telescope to try to do this today? Well, there are two main problems. One of them is known as inner working angle. This is the minimal angular separation required in order to block the star's sunlight without blocking the planet itself. And this is required to observe the planet during its crescent phase in order to then observe something like this. This would not work with any of the telescopes we have right now. And even with some of these proposed telescopes, in order to observe this, there's going to be a very strict distance limit. So for example, for one of the previous telescopes I showed you, this might be visible at something like 60 light years, but no more than that. Which is still great news because TRAPPIST-1 system is technically much closer to us, which means that the glint from those planets might become visible. But the second problem is known as photometric precision. We essentially need sufficient signal-to-noise light curves in order to retrieve multiple surfaces reliably, with simulations suggesting we need at least 15% precision when it comes to these observations. But because a lot of stars are extremely bright and reflections from planets are extremely dim, at the moment most observations from space telescopes end up with much lower precision. And so this is something that might be solved in the future, but not yet. But despite these challenges, the science here is quite solid, which means that there is a lot of optimism for one day discovering one of these liquid ocean worlds somewhere out there, with modern estimates suggesting that anywhere between 1 to 10 habitable zone exoplanets orbiting nearby stars could potentially be assessed using this technique in the next 2 decades. But it's really the K-type and M-type stars with much more compact habitable zones that could actually offer much better planet-to-star contrast ratios, thus providing us with higher chance of finding these ocean worlds. But at least it's great to know that we have one major technique that could be used to definitively discover some kind of a large body of liquid somewhere out there. This very specific multi-phase mapping technique that, unlike previous techniques, can be used to analyze the reflections of light from the surface in order to distinguish genuine oceans from other phenomena like clouds and ice. And if one day we actually do discover an ocean somewhere out there, that by itself is going to be transformative, moving us beyond theoretical habitability into the realm of concrete evidence, and thus bringing us so much closer to the answer of, are we alone in the universe? But at least for now, until we have those telescopes, or until someone else comes up with a different technique to use current telescopes for this, that's pretty much all we know. Check out all of the links and relevant studies in the description below. Thank you for watching, subscribe, come back tomorrow to learn something else, support this channel on Patreon where you can find additional videos without any ads and can DM me directly, or by joining the channel membership that grants you early access, or maybe by buying the Wonderful Person t-shirt you can find in the description. Stay wonderful, I'll see you tomorrow, and as always, bye bye.